Hi.ขอบคุณครับ All right, so let's continue on from lecture 7 and we'll switch gear a little bit. As I said, this doesn't go into the final. Oh, my bad. It doesn't go into the midterm. Does not go into our midterm. And this is basically on the final. All right, so next week we have our midterm. We did the review already. We go through the sample exam, and the material today actually is supposed to come after the midterm, but because of logistic and everything, let's actually start the other significant part of determining the performance of your computer, right? So for those of you, well, I guess everyone buy a computer nowadays, right? And you have a computer. The fact that you can join this meeting is because you have some form of a computer. It can be your laptop, a desktop, your tablet, or even your phone, right? Everything behaves, fundamentally, they behave the same way. There's a processor side, right? The CPU, and there's a memory, right? And the memory, it's like right now we're going to start to transition into the concept of the memory hierarchy, which I would explain what I mean, right? But from the programmer view, right? The programmer, ideally, what you want to see is the abstraction of the memory. What do I mean by abstraction, right? As a programmer, you would enjoy the benefit of unlimited memory. You want to be able to program without thinking much into how much memory has you been using. You also want to have contiguity. What does contiguity means is, imagine an array. Imagine an array. I have an array from A of 0 to A of 1 million, right? What can I assume about the location of the elements of A? What can I assume about the location of each element of A? So in my memory, right? In my memory, which basically looks like this. The entire array A is going to basically be contiguous, right? Inside this region, it should have the contiguity, right? Is it clear about what I mean by contiguous here? Basically, whenever I use my data, visually, I should be able to see this connected block of data from this single unit of the variable that I'm storing the data, right? It should not be the case that like one byte is here, the other byte is at a totally different location from your main memory, right? Why is it the case? So think about what will happen if you have two programs running, right? Basically, they run concurrently with allocation and deallocation. If you don't have contiguity, what can happen? One thing that can happen is basically your program has to break your array into two different regions, and how you're going to manage that, right? It's going to be a pain to manage this part, right? So from the programmer point of view, what you want to see is we want to see the virtual memory. Anyone here familiar or heard about this word before? Can you raise your hand if you've heard about this word, virtual memory, before? Anyone? Okay, for those of you who heard about the word before, good. And we're gonna do a refresher on these concepts and why are they so crucial to every single modern day computer and every single modern day program and applications, right? We'll dive into why is it there, what they are for, and why are they important, and also why sometimes it actually can make the computer run slower, right? What are the overhead of applying virtual memory? The operating system and the hardware basically would work together, right, to give this illusion. So inside the hardware, anyone here buy your own computer before, like the one that like you have to assemble your computer? You buy a CPU, motherboard, DRAM, like different parts, and you put together before. Thank you. So basically, if you did that before, right? If you did that before, one thing you might have realized is when you buy DRAM, they are physical thing, right? They actually have physical chip, like the black thing inside DRAM that you see. Those are chips that store data, right? So these are physical stuff. How do we actually allow, right, the program to use DRAM? And what is the method, right? So we're gonna learn in today's class as well as next or after the midterm. So that will be the next 2 weeks. But let's actually think about the goal of the main memory. What do we want in the main memory? Can someone tell me what do I want out of DRAM? What would be the perfect DRAM? What do I want? If I buy DRAM, what I want? Yeah, it should be big, right? And it should be fast. So that's always like you can be greedy, right? I want a large memory and I want them to be fast. So when I said fast in DRAM, what I mean is maybe it's zero latency. Whenever you want to access DRAM, the data is right there in the next cycle, right? Seems perfect. So it may be data access, right? Takes one cycle. You also want it to be big, right? Large enough, right? Anyone wouldn't prefer 1 terabyte of memory rather than I have 16 gigabytes, right? Wouldn't that be better? So let me ask you this. If I can come up with a device that can give you maybe 512 gigabyte of memory, while I sacrifice maybe like 10% performance, would that be a good thing? Would you like that, actually? Would you like that? And I think everyone would agree that, hey, that's going to be awesome, right? I can run many more things in parallel. I can store my data, right? And to be honest, we are basically from the hardware side and the material science, right? Side of things. We are basically trying to come up with newer devices that would give you this illusion. You also want zero cost, right? Ideally, I mean, I want to be able to like get memory every time I want memory, zero cost. You want also high bandwidth, right? You allow multiple parallel memory accesses in parallel, unlimited bandwidth. Wouldn't that be great, right? But the problem is these demand conflicts with each other, right? If you want memory to be big, right? It's likely to take longer to access the memory. If you want a fast memory, it's likely to be expensive. If you want to have a high bandwidth memories are probably also expensive, right? Anyone here heard about the word 3D stacked DRAM? Anyone here about this? 2.5D. Anyone hear about these two things? So if you haven't heard about it, anyone buy a GPU, like a high-end GPU that came out like last year or 2 years ago? Anyone bought that before? Or anyone like, oh, are those Optane? Great question. Optane used the other tech, well, it does support, I think, 3D Stack if you want to use that as L4. Optane in particular support the other technology called non-volatile memory. We'll cover that after we cover DRAM. So these are different technology. 3D stack DRAM is more of the still DRAM, but instead of having them, like when you buy DRAM, you see this thing, right? That is like memory stick, right? That has this chip, right? So these chips are literally where you store the data. 3D stack DRAM means that I'm going to put this chip on top of each other. So can you imagine some of the problems that can happen if I put chip on top of each other? anyone here owns like a Samsung mobile phone or like some of those phones that you can grill things on the phone and it actually cooks stuff? I guess I shouldn't name any brand because multiple multiple different phones can do that. One of the problem of putting chip on top of each other is heat, right? So how you're gonna deal with heat dissipation, temperature, right? The higher temperature you have on the chip, the more error you're gonna have on DRAM. When you have error in DRAM, what you're gonna run into is blue screen, essentially. So these days, your GPU, the top the shelf GPU, these are actually shipped with 3D stack DRAM, or in some version 2.5D, where you have the chip actually tiled next to each other. These give you a lot higher bandwidths. So you can do parallel access. But these also, because these are new technologies, actually not easy to produce, so it's going to be expensive. Great question. So we can discuss that when we talk about DRAM, but temperature does have a lot of effects on DRAM. A quick thing, imagine electron. What happens if I put heat on an atom? What will happen? Heat are energy, right? So basically, I'm gonna give energy to electrons. Well, one thing that can happen is they would move out. They'll move around. So your DRAM lose. Sometimes they lose charges. Sometimes the cell itself, because it gets the heat, it loses the ability to actually hold the data. So sometimes you're gonna have bit flips, right? So the bit flips can be bad because it makes your data wrong, right? Imagine you run something in Windows and your data is corrupt. What are you gonna run into is blue screen, essentially. If it's on your application program, the program would crash, right? So these are things that temperature can actually make impact to basically user experience, right? Because of DRAM's not as reliable. So anyone here heard about this word SRAM versus DRAM? Anyone heard about this SRAM before? So SRAM and DRAM are both common type of memory cells that we use in order to store data, right? And there are differences. The trade-off in general is SRAM is faster. It's actually a lot faster than DRAM, but it's big. So to have like 512 bytes of DRAM, which means that size, you can probably access your data in less than 1 nanosecond, or a kilobyte or megabytes of DRAM where you can access the data between 1 or 3 nanoseconds. These are expensive. DRAM is much cheaper. DRAM is much cheaper than SRAM. But the problem is the benefit is you use fewer transistor. So this is SRAM is 6 transistor per 1 bit of data. This is basically 1 transistor, 1 capacitor per 1 bit. So do you imagine why you might want to scale the transistor size to be smaller and smaller? Because you can keep packing this thing, right? Everything here costs a transistor or more. So when you have DRAM, they are cheaper. But if you look at, let's say you have a gigabyte of DRAM, this will take 10 to 15 nanoseconds to access these data. And we'll actually, in a few lectures, we'll learn why is that range here. Why is that 12 nanoseconds sometimes, and sometimes 50 nanoseconds. We will also cover emerging memory technology like 3D stack DRAM that I mentioned, or non-volatile memory that's used in Intel Optane, right? But for now, can we get the benefit of everything, right? We want to be greedy. So let's put that as a goal. We want fast and large memory, right? Fast and large memory. For those of you who buy a CPU before, any specification on the CPU besides the clock speed that kind of jumps out to you that they always list? So when you buy a CPU, what will the manufacturer tells you about the chip? Can someone list that out? What would be the different specs that you see on the CPU spec sheet? The cache, right? The cache. It can be level 1 cache, level 2 cache, or level 3 caches. So these are how you can get the best of both worlds, right? These caches are smaller memory that you put in on the CPU. And the idea is you want to be able to have a fast and large memory. So let's have multiple levels of memory. This is called the memory hierarchy, where you have the really small SRAM cache for the lower level SRAM. The first level, if I want to get my data, I'll first search this really fast memory. Then I'm going to have the L2 and L3, which are bigger, but it takes a little bit more time to access the data, followed by a much bigger DRAM at the end, right? So when you have a much bigger DRAM at the end in your computer, well, all your data is going to be in DRAM. What should we put in a L1, L2, and L3 caches? Frequently used data that you know you're going to use it a lot, right? Data that you're going to use it a lot. So here's the kind of like the overview of what we call the memory hierarchy, right? You have the CPU core. You have the CPU core. Inside the CPU core, you have our friend register, right? Register file. So this is what we learned through lecture 7, right? 1 to 7. There's a CPU, there's a register file, and they want to process your instruction. One thing that we haven't really talked about is what if you have a memory instruction? What happened? What's going to happen when you have memory instruction? When you have a memory instruction, it means that you need the data from your DRAM. But with the memory hierarchy, because you have the really fast L1 cache, you first look and see if your data is there. If it's not there, then you go to the L2 cache. If it's not there again, then you go to the memory, for example, or you can have L3 and L4, right? In a large supercomputer, they typically have an L4 there, so before you go to DRAM. In order to make sure data access is really, really, really fast, right? Really, really fast. So these are what we call memory hierarchy. Any questions so far? มีคำถามไหมครับ Any questions before we proceed onward?
L1 นี่มัน L1 L2 L3 นี่หมายถึงเป็นไซส์ที่ใหญ่ขึ้นเรื่อยๆตามเลขใช่ไหมครับ
ใช่คือส่วนมากมันจะใหญ่ขึ้นเรื่อยๆเพราะว่าอะไรเพราะว่าเหมือนกับว่าผมจะเปรียบเทียบอย่างนี้so let me make this comparison, right? Let me make this comparison. Think of a cache as so let's say I want to buy coffee beans. I want to make coffee. Where would be the first place I'm gonna search for coffee bean? Yeah, แบบผมอยากกินกาแฟผมจะไปหาตรงไหนก่อน
คาเฟ่ครับ
โทนี่ตอบได้ถูกต้องคาเฟ่เนี่ยเดี๋ยวจะเป็นเลเวลต่อไปสเต็ปแรกเลยผมขี้เกียจออกจากบ้านผมก็จะไปดูว่าตู้กับข้าวผมมีกาแฟหรือเปล่านึกออกใช่ไหมครับอันนั้นคือ register file. So let's imagine your storage cabinet as a register file, right? If my data is there, I'm gonna get it from there. But your storage cabinet cannot store every single thing. So where's the next place are you gonna go to? Now, as Narongret said, nearby cafe, right? I'm gonna go buy coffee bean from nearby cafe. So imagine that'll be the L1 cache, right? If I'm really lazy, I want to get it really quickly, I can go to nearby 7-Eleven or Family Mart, right? They're gonna sell coffee. That's fast, right? But the problem with these nearby cafes, sometimes they run out of coffee bean occasionally, especially if you go to like 7-Eleven, right? So what would be the next step? What would be the next place you're gonna search? สมมุติผมไปคาเฟ่แถวบ้านไม่มีกาแฟไม่มีเม็ดกาแฟขาย ผมจะไปที่ไหนต่อ
ซูเปอร์มาร์เก็ต
ก็จะไปซูเปอร์มาร์เก็ตขนาดใหญ่หรือพวกร้านกาแฟขนาดใหญ่ที่เขาทำเป็นโรงคั่วนึกออกใช่ไหมที่พวกโรงคั่วที่มันขายแบบเป็นถุงๆมาให้เราอ่ะ so I'll go to the next step, right? Imagine those are much bigger, right? So it's like a larger level of cache, but it take more time to go there and access the data, right? And then if I cannot find it, what do? I would cry, right? But then I will guarantee that if I go to like a coffee bean farm, let's forget about food delivery because that kind of break our analogy. But the next step would be like I would go to a coffee farm, right, and get it from there, right? I can go to the farm to the north or to the south. So there are actually multiple awesome coffee beans that I discover that are really, really good in Thailand, right? I can get it from there too. And you can imagine it would take even more time, right? That would take even more time to access my data. So imagine those are kind of like DRAM. You don't want to go there that often, right? But you almost guarantee your data is there. อันนี้เห็นภาพไหมครับว่ามันต่างกันยังไงว่าทำไมเราถึงต้องมีขนาดเล็กตามด้วยขนาดที่มันใหญ่ขึ้นเพื่อที่จะได้บอกว่า ถ้าอันไหนใช้เยอะๆเราก็จะไปแค่เนี่ยไปเซเว่นก็ได้ละได้ data มา
เห็นภาพครับ
so let's imagine another scenario. Let's say you have to run the local shop, like 7-Eleven, Family Mart, or even ร้านโชห่วยแถวๆบ้านอย่างนี้นะครับผมน้องเป็นเจ้าของร้าน so how would you stock your shelf? What would be the best strategy that you're gonna use to find what to put in there? ผมจะสต็อกเซเว่นผมใช้ strategy ไหนดีไม่เอา strategy เจ้าสัวสั่งมานั่นคือไม่เกี่ยว เอาเป็นร้านโชว์หวยก็ได้ผมจะเลือกว่าจะสต็อกอะไรบ้างผมจะเลือกยังไงดี
Some popular thing people buy.
Exactly, right? So you from the chat, so that's a great answer. You're gonna check which item get used the most often. And that makes sense, right? So the strategy is, well, I'll check, hey, people buy milk a lot, people buy bread a lot, people buy like these type of snack a lot, like Lay's or other snacks. People buy soda a lot, so I'm gonna stock those things, right? Because a lot of people comes and buy it. So we can apply the same strategy for our caching policy too, because I have limited space, right? So I need to figure out what I'm gonna stock to make sure if I drop by, if a customer drop by the cache, it's likely that I can find my data. So that comes to the topic of, I guess, the first go through caching basics, right? It does take advantage of two key properties of your program. The first properties is called temporal locality. This is simple, actually. Temporal is time. Like temporal is time. What it means is I access this variable. It's likely that I'm going to access it again. Why is that the case? If you look at this code for I equals 0, I is less than n, I plus plus. How often am I going to use the variable I? Just look at this loop. Without anything in the loop body, you can see that the variable I and n are going to be used really often, right? At the end of the loop, I need to increment I and compare that to n. And it's likely that inside the loop body, you do something with the variable I as well. So these are temporal locality. These ideas actually been kind of brought about in terms of how to manage the data back in 1965, right? So if you go back to our lecture, the first lecture, you remember around what time when is the first computer invented? In around what year? I think it's 1930, like late 30s and early 40s, right? 20 years afterward, we now start to think about how to store data efficiently. To see how the computer start to evolve into more and more powerful machine, right? You can also take advantage of what we call spatial locality. Spatial locality is not time, it's space. Like spatial is space. What does it mean is, when I access something, I'm likely to access something next to it as well. How many people write a loop this way? And you do something with A of I. You do something with A of I. So that the next iteration, you are going to access A of I plus 1 and then A of I plus 2, right? Oh, okay. Thanks for the question. That was kind of like almost like a concept of a cache back in the day. So back in the day, there's no concept of the cache until that paper. People have storage. People have CPU, and we are basically, as an engineer, trying to invent how do we make sure you can access data really quickly, right? So the paper kind of introduced the concept of, hey, let's have this method to dynamically allocate the storage for data that are likely to be used again. And look at 3 years later, we have the word cache. 2 years later, we have the word cache. And that paper then observed that the way you write program have this pattern. You access something and you're likely to access the next item right away. Right? So caching take advantage of these two observations. This is really, really, really common in research. When you observe something, you can use that observation for your hypothesis as well as your solution, right? So the basic of caching design take advantage of these observation of how you write a program. So to manage data in a cache, now with the observation, we have a way to guess which item am I going to use more often, right? It's either the same item again or the item next to it, right? So the way you manage the data in the cache, there are two different ways. The first method is to have a manual access. Anyone programmed using CUDA on GPU before? Anyone did this before? So you might have actually noticed that the GPU allow a manually programmed cache. So you can actually pin some of the data to those cache because you know when you program, hey, I'm going to need to reuse that. So you can manually manage the data. Inside the GPU's shared memory, you can actually configure the cache so that you can program what to be put in there. This means the programmer would manage the data across all the cache level, and in general, it's going to be painful for the programmer. So it's not a good idea in a general sense, right? It can be useful if the programmer knows what they are doing, right? But sometimes when you code, like I don't want to worry too much about whether my data is in the cache or not. So ideally, most of the hardware should automatically manage your cache, right? It should automatically manage your cache inside the chip. Why is that the case? Many of the things you're doing is in the microarchitecture. It's not even exposed to the programmer, to the ISA, right? Cache is one of those that never get exposed to the programmer. It's in the microarchitecture. Why is that the case? Because we manage this automatically for you. But knowing how the hardware manage the cache can make your program faster. Anyone heard about this technique called block matrix multiply? Anyone heard about this technique before? So block matrix multiply is you do matrix multiply, but instead of multiplying this entire row to one entire column, you do one block at a time so that they fit in the cache. And that way your program can be way faster, right? And if you work on machine learning, you know how useful matrix multiply is. So let's dive into the concept of caching, right? So let's first dive into this concept of caching. And this lecture, I'm gonna do something a little bit differently because I will first define some basic terminology. Might be a little bit boring, but I need to define basic terminology. So at an hour load and store instruction, right? What's the typical size of load and store? What are the, like, when I access my data, how big is that? Well, it can be 1 byte, a couple of bytes, 1 data word, right? 4 bytes is really common. For 8 bytes, like 1 data word, 1 word is really common. But it's basically in the bytes granularity, right? When you do caching, caching has also its own unit of data, and we call this a cache block. A cache block typically is larger than a size of the load. A cache block is a unit of data that typically are bigger than the size of one load. Each cache block is mapped to the same location of the cache. And access to a certain part of the cache, basically when you have an address, they're gonna go just to a certain part of the cache in order to find where is my data. And when I find my data, I call that a cache hit. When my data is not there, I call this a cache miss. Cache miss. So here's my design choice, right? What do I store in the cache? Can I store instruction in the cache? Anyone remember our fetch? Our fetch. What does fetch have to do? Where do I fetch my program from? Where's your program? It's the main memory, right? And so far, we assume fetch take 1 cycle. If I tell you that main memory take at least 10 nanoseconds, is it possible to fetch it in 1 cycle? If we don't do anything, you cannot, right? Because the memory is slow. So can you put instruction in the cache? Can you put your data in the cache? Can you put virtual address translation data in the cache? We'll discuss some of these design choices, and to spoil you, right? We have instruction cache, data cache, and the translation lookalike buffer that's used to cache the last item here, virtual address translation. We use cache everywhere in your computer. The next thing that you have to decide is, how am I going to place data in the cache? I have this blob of memory. How do I manage it? What's the easiest way you can manage it that are viable in hardware? When the cache is full, how do I pick what to remove? Which one to kick out, right? Which one to kick out? That's another design choice. How are you going to deal with writes when there are many core and many layers of your cache, right? How are you going to deal with writes? Also, things like, should I manage the cache in cache block granularity? Or should I subdivide them into sub-cache block? Or should I manage them in a bigger than cache block granularity? And those are all design choices. And this is one of the tasks that computer architect has been kind of designing and then design it again for new application, design it again for new application. And now we have things like serverless, GPU, and heterogeneous processor. We also design the cache again, right? Because these things have so much impact on performance and the program that you're running. So let's go through the most primitive form of the cache, right? The first thing that are in the cache is what we call a tag store, a tag store. What did we use the tag for? Remember our out of order lecture? What did we use the tag for? Why do I need a tag?
To be like a virtual register.
It's basically, yeah, yes. So it's to tell, right? To tell, is that your data? Think of the tag. Always whenever someone said label the BC register, that's for the out of order, right? That's all for the out of order lecture. We use a tag to specify who is producing this value. Tag can be used to identify something. So we use the tag, the same concept in the cache. But now it stored the address. Part of your address is a tag. It's used to check, is that your data? If the tag doesn't match, it's someone else's data. That's what you can use to search where your data is and whether your data is in the cache or not, right? The other part, obviously, you need a data store. That's where you store the actual data. This is where you store the actual data. So basically, you use an address, right? Every single data have an address. You use an address of that data to search in the tag store in order to retrieve the data in the data store, right? So tag is to identify whether that's your data or not. Data is where the actual data is located. So the next question is, well, I have a tag store. What should go in there? What should go in there? The first thing you should go in there is a valid bit. Can I use this data? If it's 1, yeah, you can use this data. If it's 0, it's some junk data, don't use it. So that's a valid bit. You also need the tag bit. The tag are bits that correspond to some region in your address. And you can use the tag to search for the correct data that you are looking for. And don't worry about this terminology. We'll go through some example. I need to define things first because when we go through examples, it requires a lot of new terminology. It also contains replacement policy bits. We'll talk about this later, but it kind of governs how should we kick things out when the cache is full. An array for dirty bits. We also talk about this later. When we talk about computer system and computer architecture, whenever something is dirty, it means that someone write the data over this. It makes sure the data are consistent. Make sure the data is in the you have the most correct and the most recent version of your data. So now that we know the name and definition of these terminology, let's start with the cache organization. So the cache contains multiple cache blocks. So actually, let me ask you this: like anyone here, how many people have been through some lecture that talks about the cache in the undergraduate? And can you raise your hand? I just want to double check how fast can I go. How many people might have learned this in undergrad but already forgot what they are? Can you raise your hand? How many people have never heard of this? All right, awesome. So this is good. So I would make sure that we cover this. This is basically, to be honest, most computer science and computer engineering everywhere in the world, there would be at least 1 or 2 classes that cover caching for the undergraduate. I don't know what happened in Thailand. And I have I'm gonna critique this because this is really important. But I'm gonna cover this for sure because that's what I assume. That's why I make the slide this way, right? It starts from the basic and it should build this foundation so that you know what are they and how do we use it. So the way you organize the hardware cache in the CPU is you have multiple cache blocks, right? Each block belong to a cache set. Again, I'm going to show an example. Right now, I just want to describe things. I have the cache. A cache is like a block of memory that I can store my data. The way I would organize this is I would break the cache into multiple cache blocks. Multiple cache blocks would be grouped into a cache set. What is a set? What do I use set for in mathematics? What is the set for?ของใครเลขเรามีเซตไว้ทำอะไร It stores unique value, right? So over here it collects, basically it collects multiple cache block. Each memory, the address is mapped to certain sets. So this is like a visualization. Let's say the cache right now contain 16 cache blocks from cache block 0 to cache block 15. And let's say there are 2 cache blocks per set. Let's say there are 2 cache blocks per set. You can visualize it this way. Let's say I have an address called address A. This address A would map uniquely to just one set. And it guarantees, based on the address, it guarantees that it has to be in that set. If it's not there in that set, it's not there in the cache. It's not there in the cache. ให้ขอยกตัวอย่างภาษาไทยอีกตัวอย่างหนึ่งสมมุติว่าเราเรียนชั้นประถมแล้วกันชั้นประถมก็จะมีหลายๆห้องใช่ไหมครับป .1 ทับ 1 ทับ 2 ทับ 3 ทับ 4 ทับ 5เนาะนึกภาพออกป่ะแล้วสมมุติเราจะไปหาเด็กคนหนึ่งบอกว่าเด็กชื่อเนี้ยวิธีที่หาง่ายที่สุดบอกว่าเรารู้ว่าน้องคนนี้อยู่ป .1 อ่ะแล้วเราจะไปหาว่าน้องเขาอยู่ที่ไหนเราจะใช้วิธีไหนในการหาครับเราจะเดินไปหาทุกห้องเลยป่ะหรือว่าเราจะดูก่อนว่าน้องเขาอยู่ห้องไหนเราก็จะไปดูก่อนว่าเด็กคนนี้อยู่ห้องไหนเนาะเพื่อที่จะได้ไม่ต้องมานั่งหาทุกห้องแล้วก็ไปที่ห้องนั้นก็เหมือน cache set แล้วเราก็เอาชื่อของคนที่จะหามาดูว่าคนชื่อนี้อยู่ในตรงไหนในห้องนี้อันนั้นคือ tag อันนั้นก็คือให้เทียบกับว่าเป็น tag so let's actually go through some cache organization example let's say I have the wrong letter typo I have the cache that are how big let's say it's 4 kilobyte cache and cache block is 64 bytes how many cache blocks do I have here in my cache how many cache blocks do I have can I store in my cache Yeah, 64, right? The way you do this is 4 kilobytes divided by 64 bytes. That's basically 64 cache block. And let's say number of cache block in a set is 4 blocks. How many cache set do I have here? So I can contain 4 blocks per set. How many sets do I have in my cache? $16, right? 64 divided by 4. So this is, let's say this is your cache, right? This is the set ID that start from 0, 1, 2, 3, 4, 5, down to 15, right? You can imagine then each one of these is like multiple rows. There are in total 16 rows. And then inside the row, right, it's going to be cache block. And there are 4 in total that can be stored into this set. Right? So the organization is just simple, like what I just showed you. So if you see this, for example, on the exam ตั้งสติก่อนครับแล้วดูขนาดเสร็จปั๊บดูว่า cache block หนึ่งขนาดเท่าไหร่จับมันหารกันเราจะได้จำนวน cache block ทั้งหมดเราได้จำนวน cache block ทั้งหมดเราก็ดูว่าเซตหนึ่งมีกี่ cache block ก็ตั้งสติอีกรอบถ้าเซตหนึ่งมีเท่านี้ cache block เราก็จะรู้ได้ว่ามีกี่เซตมันก็จะเป็นสมการย้ายไปย้ายมาได้ so once we know the organization we then know that each address on your machine would map to one of these sets. How do I figure it out? The next step is the cache lookup. What do I mean by cache lookup? You need to think about it this way. You divide every single address, right? And you just look at the bits for your address. And there are basically 3 parts inside the address. There'll be the part that is the tag. Another part that used for the index bit. The index bit basically is the same as your set ID. So if the index bit is 10, it means it go to set 10. If the index bit is 0, it go to set 0. If the index bit is number 15, it go to set number 15. It's as simple as that. The index bit tell you what set do I go to. The tag bit tells you whether your cache is there, your data is there or not. Again, let's say this is your address. So can someone give me some address, maybe 16 bits long? 16 bits long. Or you can use hexadecimal number, anything. But it's let's make it 16 bit. Wait. Okay, 404. Let's say address is 0x404. That is going to be 0, 1, 0, 0. That's the first 4. O, and 4. And apparently I cannot count. Sorry. So the way this is organized is there'll be some lower bits that will tell you which byte am I accessing. And these bits is the log of the cache block size. We will cover the fine detail in the next slides on the method to do this. And then the next part is going to be the index bit. So let me ask you this. If I have 16 sets, let's say I have 16 sets, how many bits do I need for the index bit to be able to tell from set 0 to set 15? If I have 16 sets, how many bits do I have so that I can be basically so that I can represent set 0 to set 15? Four bits, right? Why is that the case? I need to be able to represent the number 0, 1, 2, 3, 4, 5 up to 15. You need 4 bits for that because you need log of 16. The rest, everything here are the tag bits. Again, these kind of questions, just calm down, all right, and think about this. Where are the index bits? Where are the tag bits? Why are they important? Why are they important? I can write a program such that I put the index bit and tag bit in certain way and I never get a cache miss. I can also by accident do the same thing, but the inverse of that. Every time I access the cache, it's gonna be a cache miss. So your program is a lot slower, right? Once you know the address, you can guess whether what set does your data is going to, and how do you make the most use of the cache. So let's kind of formalize how to get the index bit. Again, each address would point to any unique bytes in your DRAM, right? Address 10 would point to byte 10 in your DRAM. Address 1025 would point to address 1025 in DRAM. So inside the cache block, right? Inside the cache block, these contains data. Typically, these are 64 bytes, but in the older machine or smaller machine, it can be 32 bytes. Right? It depends on the configuration of the machine, and you can actually check it out. So the cache block contains multiple bytes of data. So the least n significant bits, right? So let's say this is your address. This is your address. The last n bits are used to tell which byte am I accessing from the cache block. Which byte am I accessing from the cache block? And the size of n, how many bits, is basically log 2 of the number of unique locations that you can access in the cache block. So let's say you have a cache block of 64 bytes and you can access every single individual bytes. It means you need n equals log of 64, which means n is 6 bits. If I tell you that I can only access byte 0, byte 2, byte 4, byte 6, like every 2 bytes, then in the 64-byte cache block, there are 32 unique locations that my address can access, right? Then the number n can be smaller. But typically on most machines, this n is essentially the log of the cache block size. Log of cache block size. The next m least significant digits are reserved. What are they for? Is for the index bit. The next m bit, which is the log 2 of number of cache set, is the index bit. I typically call this byte in block bit. I typically call this index bit. And then the rest are the tag bits. The rest are the tag bits. The rest are the tag bits. And that's all. That's all. So let me pause here quickly for now. Any questions about how do you, let's say I give you an address. How do I figure out where is the tag bits? What are the set ID? What are the index bits? มีคำถามไหมครับ มีคำถามไหมครับ หรือว่าพอผมพูดถึงกาแฟทุกคนเลยอยากกินกาแฟ จะคว่ำแล้วผมพูดเรื่องแคชอยู่ได้ถ้าไม่มีคำถามขอต่อนะครับ Alright, so now that we know how to identify index bit and tag bits, again, remember these are tied to your address. So when you write a program, it can impact the cache hit rate. Why is that the case? There are different ways you can design the cache. One of the ways is called direct map cache. Direct map cache means that that's one cache block per set. Any address, it only go to one single location, one cache block per set. Inside a set, there's something there, and there's only one cache block in there. When you have a load and store, if I have one cache block per set, is there an index bit? Do I need an index bit? You still need an index bit. The size of the index bit is still the number of set. And then once you have the address, you check the tag at the set that you are trying to access. If the tags are compared, if it match, it's a cache hit. Otherwise, it's a cache miss. If it's a hit, I return corresponding data. Otherwise, I search the next level of the cache. So let me ask you this question. Can I accidentally write a program on a machine that uses the direct map cache and I get 0% hit rate? Can I do that? Can I do this? That's a yes or no question. What do you think? Can I write a program that never hit in the cache? Even though I loop around, I loop and try to access series of data, but I get 0% cache hit. Actually, let me argue something more specific. Let's make sure my program only do this. Loop. Access. Address. A followed by access. Address. B. And that's it. That's the only thing I do this loop, but I do it 100,000 times. Can I figure out the address A and B in a way that I never hit in the cache? Even though I only access 2 pieces of data, but I never hit in the cache. Is that possible? เป็นไปได้ไหมครับผมมี direct map cache แล้วผมเขียนโปรแกรมนี้ไม่ทำอะไรเลย loop เนี่ย loop เอาค่า a b a b a b a b ไปเรื่อยๆแล้วผมการันตีว่า cache มีขนาดเกินขนาดของ a กับ b รวมกันแน่ๆแต่ผมสามารถเขียนโปรแกรมให้กลายเป็นว่ามันไม่อยู่ใน cache เลยได้ไหม So there's one answer say no, it's impossible. Anyone want to say yes? Well, let's assume program always, this is hardware managed. So we always try to store everything in the cache. Every time you have an app, you try to store that in the cache. The answer is actually yes. So let me draw it out, right? Let me draw it out. So this is your direct map cache, right? This is set 0, set 1, set 2, set 3, blah, blah, blah. In a more ideal case, right? In a more ideal case, one thing I can do is, well, if I'm lucky, A is going to be here, B is going to be here, and I'm done. Every time I go to the cache, I get a cache hit, right? อันนี้ทุกคนยังเห็นภาพเดียวกันนะสมมุติถ้า A ไปที่เซต1 B ไปที่เซต2อันเนี้ยผมจะได้ cache hit ตลอดเวลาอันนี้ยังตามทันกันอยู่เนาะถ้า A กับ B ไปคนละเซตกันแล้วผมลูปแค่เนี้ย A B A B A B A B หนึ่งกรณีเนี้ยมันจะฮิตทุกอย่างในแคชหมดเลยเป็นโลกสวยงาม so can I make it such that A and B go to the same set? Can I do that? Can I write a program such that by accident A and B go to the same set? Can I write a program such that for the address of A, right? The tag, for example, is 10. The set ID is 2, and then address B tag is 20, and the set ID again is 2. What happened here? มันจะเกิดอะไรขึ้นถ้าผมเขียนโปรแกรมแล้ว address ของ A กับ B อ่ะพอผมทำ breakdown มาปั๊บมันไปเซตเดียวกันไปเซต2คู่เลยแต่ tag มันคนละ tag มันจะเกิดอะไรขึ้นถามคำนี้ก่อนเซต2ตอนเนี้ยเก็บค่าได้กี่ cache block หนึ่งเซตเก็บได้กี่ cache block สำหรับ direct map cache 1 cache block ตอนนี้ผมมี กี่ cache block ที่กำลังจะพยายามใช้เซต22 cache block เพราะฉะนั้นผมลูป A B A B ตอนผมเข้า A ปั๊บผมก็จะพยายามโยน A เข้าไปใน cache block ที่เซต2แล้วพอผม access B ปั๊บก็ไปดูใน cache อ๋อ A อยู่ตรงนั้นก็เตะ A ออกเอา B ใส่เข้าไปแทน Exactly. So in this case, your program would kick the older thing out and replace it with the new thing, right? So that way, you basically doesn't benefit from the cache. This problem is called thrashing. Thrashing basically means that I still have space in my cache, but I kick something out because there's no room in a set. Too many things are trying to access that set, so you get a cache miss. To fix this, so what should you do to fix this problem? What's the most obvious way? Well, I guess there are two things that are pretty obvious that you can fix. Any idea? Let's brainstorm, right? Let's brainstorm and see how can I fix this? So can I change the way I access them? Can I change the address? Change B to some other address? Can I do that? So that it go to a different set. Yeah, you can modify your program, right? So that it goes to a different set. How about, can I then use more than cache, like make sure my set can contain more than one cache block? I mean, in the context of this class, we design hardware. So the answer is yes, we can redesign the hardware, right? How do we do that? This is a concept called set associativity, which basically means that in a set, there are n cache blocks. Basically, within the set, there are n cache blocks. Because the problem of direct map cache is data access always map to the same location, to the same set. And if the tag doesn't match, then you kick the other thing out and you have a cache miss. So in the other way, why can't you just store multiple multiple cache block within a set? So cache block is a single unit, but now cache set contain multiple cache blocks. This is called the set associative cache, right? Basically, n set per n blocks. Again, I'm sorry. N blocks per set. Right? So when you have n way set associative cache, what it means is you have n blocks per set. And this is called set associative cache. The downside of this is when you want to go and check if my data is in a set or not, now you have to start comparing things. Is the tag match block 1? Does the tag match block 2? Does the cache tag for my address match cache block 3? So on and so forth. So these actually does take more time, a little bit more time to access. So the trade-off is if you put more cache block in a set, it takes more time to search. So most of the time, if you look at the cache design, right? The cache design, the set associativity would kind of vary between 2 to 4 to 8 to 16. But it's not going to be a high number, like thousands of set associativity. Another idea is on the other end of the spectrum, we call this fully associative cache. Basically, a cache block can be placed anywhere and you just search for the tag. There's no set ID. There's one set, everything is there. Every single thing is that one set. Which means that you have to do a lot of search to find your data, right? So when would this work well? When does this work well? If the cache is small, it can work, right? It can work pretty well. But most of the time, it's also a bad idea. If you have a fully associative cache everywhere, because it does take a lot of comparator, and it does take some time to look it up. All right. Any questions so far? Because now I'm going to transition into the more of the design elements of the cache. How do we insert the data and how should we replace the data? มีคำถามไหมครับ ก่อนที่เราจะคุยเรื่องว่าเราจะดีไซน์แคชแบบยังไงดีก่อนยังไงดี มีคำถามไหมครับ Most of the time, yes. Most of the time, the index bits are grouped together. Basically, most of the time, right? If you look at the default, I guess the default setup, it's going to be something like this: tag, index, and these are byte-in block that we doesn't really use for cache lookup. There are papers that propose like maybe we can hash this bit and this bit for the index so that we can balance out what set does the cache go to. So there are techniques that try to like spread out the cache accesses as well. And so that's a great question. And another reason why that's a great question is, I mean, to be honest, these are design questions, right? I mean, we can put whatever bits for the index. It just turns out when the way you loop around, for example, you do lower bit first. So when you spread around the cache blocks this way, it tends to like spread things around across multiple sets. And there are again proposals, as I mentioned, to kind of mix in some other bits and hash them, right? อันนี้ตอบคำถามหรือเปล่าครับ So does it help you're answering your question? ก็คือถ้าเราเปิด textbook เนาะ textbook ของ computer architecture เราก็จะบอกว่าใช่ตามนั้นแหละก็คือเป็น tag ตามด้วย index แล้วก็ที่เหลือจะเป็น byte in block อันนี้คือใน textbook แล้วก็ในตำราทั้งหลายแล้วก็จริงๆในชิปจริงๆก็ประมาณนี้แหละ
I want to confirm my understanding. So the index is used to eliminate the compiler, right?
Do you mean direct map cache, right?
In direct map, we don't have the index, right? Because each set contain one cache block.
Yep.
But in this image, we have index, so that in one set can contain more than one cache block.
Yes.
But without this index, we have to search with compiler, which take time. So that we use this index to hash, and we don't have to search, right?
Oh, you mean hashing? It's a different technique basically. So it's a slightly different cache design. You still work with set associative cache, but you can basically mix in some of the tag bits into the index, so it goes to, instead of like multiple things going to set 0 to 4, for example, it would try to spread it out across multiple sets.
Okay.
แต่ไอ้ comparator เนี่ยคือสมมุติเรามี10 cache block ในเซตอะพอเราได้ tag มาแล้วอะเราก็ต้อง compare อยู่ดีว่าcache block เราอยู่ตรงไหนให้นึกซะว่า cache set อะก็คือแต่ละห้องเรียนแต่ละห้องส่วนจำนวนของ cache block ที่อยู่ในเซตอะก็คือนักเรียนที่อยู่ในห้องเพราะฉะนั้นสมมุติห้องเรียนเก็บนักเรียนได้4 คนเราเดินเข้าไปเราก็ยังต้องเอาชื่อนักเรียนมาหาดีว่าคนนี้อยู่ที่ห้องนี้หรือเปล่าใช่ไหมแต่มันจะหาได้เร็วขึ้นเพราะมีคนอยู่แค่4 คน Imagine อีก scenario หนึ่งโรงเรียนระบบไทยนักเรียน50 คนในห้องน้องเดินเข้ามาก็บอกว่าขอถามหน่อยว่าน้องคนนี้อยู่ห้องนี้หรือเปล่าก็จะต้องนั่งหานานขึ้นนิดนึงมันก็เหมือน fully associative cache ที่จำนวน cache block ที่อยู่ในเซตอะมันเยอะมันก็ต้องหานานนิดนึงเพ ราะว่าเราต้อง imagine ทุกอย่างมันคือ hardware เพราะฉะนั้นเราก็ต้องมี comparator เยอะๆเยอะๆแล้วก็ compare เราก็ compare เป็น tree นี่แหละแบบเข้าไปเป็น binary tree มันก็จะใช้เวลานิดนึงในการ compare
I think I understand something. I think the set is like the room, and the index is like the thing that tell which student you are looking for.
So it is more like, let's say the cache block is a student in a room. The cache set is a room.
Yeah.
And the whole cache is like the entire class, which has multiple rooms, right? Then the index is the room number. So when you have the index bit, you know, okay, that student is guaranteed. If he or she is there, it's going to be in that room. Then the tag is when you enter that room and say, is this particular student here?
Okay. So the index is the index of set, not the index of
yes.
cache box in the set. Okay.
All right,
Okay,
so let me answer also Tony questions about you're wondering if the tag in front contain many tags. Okay, I'm confused about that question. I'm sorry. So the tag, let's say you have an address, right? When you allocate any data in C, in Python, the data has an address tied to that. The address is basically a hexadecimal number, right? Parts of the address are the tag. The other parts of the address are the index. So the tag is basically typically is like the rest, right? The rest of the address not used for the index. อันนี้ไม่แน่ใจว่าตอบคำถามหรือเปล่าครับ Tony, does the explanation help? Okay, awesome. So before we go into the design part, let's take a quick break before we start to think about, okay, can we come up with a different strategy to insert or to replace the data? Let's do a quick break. Let's resume at 2:25. Is that okay? Oh, that's a great question. Is there a way that you can design such that we don't have to search a cache? So direct map cache is kind of that, right? Everything is mapped to one set. And once you are there, it's only one thing in the cache, right? So you compare the tag. If it's there, it means it's a hit. If it's not there, you go to the next level. That's also, I think, recall a few like papers that talk about like different hashing mechanism that would try to like alleviate this searching and how to actually make sure data are spread out across your cache. Okay. อันนี้ตอบคำถามหรือเปล่าครับน้องพานุเทพ
I mean, we still have multiple cache within a set, but then we have an index which we can use to
figure out which one, which group you are in, right?
Yeah, which cache.
But that's basically basically that means it's the same as you break your cache set into more cache set, right?
Yeah, we can think of something like that.
Yeah, so I mean it's the same structure as having more cache sets and less than คุณพ่อทำน้ำมะพร้าวให้ and have the fewer blocks per set, right? Because the key thing about the cache set is the ability to fully search to see where you are. So you can be in the first block, second block, third block, or fourth block, or etc. inside the set.ๆ กำลังคิดอยู่ว่าดีไซน์แบบที่น้องพูดมันจะ So to be honest, right, there are quite a handful of different ways you can organize the cache. So this is something that the research community over time, right? Over time since the 1960s that you've seen from the sample paper, right? We've been kind of evolving in terms of how to design a cache, how to use a cache. We can have different type of cache. Sometimes you can also have a cache that doesn't store data as well to track, right? To track how should we change the policy based on the hit rate we see in this shadow tag and things like that, right? So let's talk about this a little bit more in after the break. After the break งั้นเดี๋ยวเรา resume ตอนบ่าย2:25กันไหมครับ All right, so let's see you guys in 4 minutes. I'm gonna go and get a little bit more coffee to make sure we are all like super active. And then after I got coffee, if I say something is too fast, let me know because I tend to do that. So if you have questions, feel free to leave it here. I'll come back quickly and do a quick Q&A before we move to the next topic. All right. โอเคครับเดี๋ยวเจอกันบ่าย2:25อีก3 นาทีนะครับ โอเคกลับมากันยังครับ I'll be back Oh yeah, so let me explain that again just to make sure it's clear, right? So this last set of bits, right? This is your address, right? This is your address. If you think about it, your address need to tell which byte, right? Which byte you're accessing. This tell me the cache block. This also tell me where's the cache block, and the cache block is multiple bytes, basically multiple bytes. There are multiple bytes in a cache block. The last part of your address basically tells is the data here in this byte, or is it here in this byte, or is it here in this byte? That's why we need to reserve those bits to tell which byte are you trying to access. So does it answer your question? All right, awesome. Also, this is my 6th shot of coffee, so if I'm going too fast of today. So if I'm going too fast, let me know. I'm gonna make sure that's not the case. All right. So the question then is, or the next question, now that we know how the cache is organized, how do I access them, right? You know how to access them. The next thing that you have to figure out is, what if the set is full? What if the set is full? How do we insert things into the cache set? And how do we kick something out of the cache set, right? For direct map cache, it's easy. Direct map cache is actually easy. There's only one thing in the set. It's full. Kick that thing out. Replace it with a new item, right? If it's a set associative cache, which means that there are multiple cache blocks in the set. If there's multiple cache blocks in the set, you basically have a choice, right? What's your choice? Let's say there are 4 cache blocks. You can pick, I'm going to kick out cache block 1. I'm going to kick out cache block 3. I'm going to kick out cache block 4. And the way you kick things out can impact performance. So here are the key issues. When you insert, how are you going to insert? What would be the prioritization of this newly inserted block? The new block in the set. Should it have high priority? Should it have low priority? Promotion, which is if I have access to something in my cache block, I have access to something in my cache block. When the data is in the cache, which block are going to be more valuable? Which block are going to be more valuable? And eviction, which is basically how do I pick what to evict from the cache? How do I pick what to evict from the cache? Which one should I kick out? Right. So let's go through this one by one, starting with the what to kick out, right? Replacement policy. When the cache is full, when the set is full, to be more specific, you need to pick which cache block, right? Which cache block to evict, basically to kick out from the cache. This is called the replacement policy. So can someone here tell me what can be some potential policy? What should be some potential policy on, I have, say, 4 cache block per set. There's new cache block coming in. I need to pick which one do I kick out. What can be some of these policy? How do I pick? Any thoughts? If you have black magic, you can do whatever you want with the cache block. How are you gonna replace things? One thing you can do is the oldest, right? Why might the oldest policy would be good here? Why is the oldest block is a good policy? There's a probability, right? Sometimes we might no longer use it because they are old. What if I say, hey, that oldest block is actually used pretty often? What do? Let's say that oldest block get reused all the time. Like the program keep reusing. Yes, that's what they do. Being sad and cry, right? Definitely one of the great default thing that we all do, being sad and cry, and then we would recover and keep coming back stronger, right? So what if that oldest block is reused often? How about something like frequency based, or the last time I used this block kind of based, or even random, right? So these are design choices. Basically, you have multiple things you can do. One of the most obvious one, random, random policy. First in, first out, these are oldest first. Least recently used means that I look at all the cache block and see, okay, I haven't used that block for a while, so let me kick it out. Even though it might be the youngest, but I never use it, I'm gonna kick it out. So that's the least recently used. Not most recently used is kind of like a way to approximate least recently used. I just need to figure out what is the last cache block did I access, and then kick a random block that's not that guy, right? Least frequently used, in that case, you count how many times you access the block, and the one that has the least frequently it's gonna get kicked out. If you have black magic, not likely to be used again, based on some black magic, right? If you can put some magic in your computer and it basically say, hey, I can predict you're not gonna likely get used again. You can predict the future. This is start to go into the realm of like black magic. You can have the hybrid policy, which is a mix of these policy, right? So we will discuss some of this and see what are the trade-off and think about how can we make a more optimal policy, right? So let's first talk about the least recently used, because this kind of makes sense, right? So this is based on both temporal locality and spatial locality. Cache that hasn't been used for a while are not likely to be accessed again, right? So the insight from this policy is as simple as this. I have the cache block and no one used that for a while, probably useless. So let me kick it out. Benefit is likely to be effective. Anyone want to think about what the potential downside of this? What are the potential downside of this policy? So let me ask you this question. If I need to sort, and if I need to find the least recently used cache block, what algorithm do I have to implement in order to pick the least recently used one? How do I get the block that is not the oldest, it's the least recently used?
You have to count and sort.
Exactly, you have to count and sort, right? Counting is not bad. You can tie counter to a cache block, right? And count up. Counter is not that expensive. Sorting is different. Sorting is a different story. We are all writing a sorting algorithm before, right? But imagine that you have to just go by with comparator, AND gate, OR gate, NOT gate, and do sorting in hardware, right? Probably not as easy. So LRU, or least recently used, is actually a good policy. But the downside is this can be pretty costly when there are more cache blocks in a set. Like 16-way, 32-way. There are 32 cache blocks you need to sort, right? It's not easy to implement a FIFO queue in hardware that can be sorted based on the time, based on the last access, because you somehow need the ability to dynamically move items in the queue, right? So this is actually can be complex to implement. What could be the solution? If the precise option is hard to implement, what can we do? We can approximate LRU, right? We can't get the LRU, we get something close, good enough, right? Because LRU is basically, to be honest, LRU is approximating what should be replaced anyway. So I guess we can approximate that again. The easy way you can do is called not most recently used. Basically, you have one bit. The last time the access to the cache set happened, you flip that bit for the cache block. The other cache block in the set would be set to 0. So let's say there are 4 cache block in the set. Cache block 1, cache block 2, cache block 3, and cache block 4, right? Then you have this one bit that say, is this a most recently used? And let's say cache block 4 is the last time you access this set. There's going to be 1. The rest are 0. So when you have the access to this block, how am I going to pick which one to kick out? If I use a not most recently used policy, I'll just kick anything that has 0 bit here, right? Anything at random. As long as you don't kick out cache block 4, you are essentially trying to approximate LRU policy. Let me ask you this. Is this a good approximation? Is this a good approximation? Does this get closer to random policy, or is it closer to the LRU policy? Can someone tell me that? Which one is closer? Any idea? Between LRU and random, which one is closer with this particular not most recently used policy? อย่าเดี๋ยวข่าวนี้ก่อนยังตามทันกันอยู่ครับว่าไอ้ not most recently used ก็คือพอผมมี cache access ใช่ไหมผมก็ mark อันเนี้ยบอกว่าเอ้ยครั้งสุดท้ายเราเพิ่ง access บล็อกเนี้ยเสร็จแล้วถ้าเราจะ replace เราก็ถีบอะไรก็ได้ที่ไม่ใช่บล็อกนี้ออกซึ่งมันก็เกือบ random เนาะคือมันก็เกือบ random policy คือ this is basically really close to a random policy so one thing you can do to improve this is to have this hierarchical design. For example, let's say you have 16 cache block in a set. Then you divide into 4 groups, right? 4 groups. Then you pick the oldest, not the oldest. You pick the one that's not the MRU from each group. And then you pick the next hierarchy so that you get hopefully something closer to the LRU. So let's say this is an example, right? Cache block 0, cache block 1, cache block 2, cache block 3, 4, 5, 6, 7, 8, 9, 10, 11. (13, 14, 15). 13, 14, 15. Then you group them into a group of 4 here, 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 and then here. Among each group, when you have an update among each group, you will say, hey, this group is the most recently used. So this group is protected. No one here would get evicted. Then you're going to pick one of the victim from the other 3 groups. In the other 3 groups, you will send in the candidate. Basically, inside this group, you have another bit to track the most recently used. So let's say This is the most recently used. The candidate for eviction would be this block, or this block. Let's say this is the most recently used, right? Then the candidate with this block or this block or this block. Or for this group, it will be this block and this block and this block. So you pick one. You pick one of this block and kick it out. The benefit of this is for each hierarchy, you only need one bit. You only need one bit. You would then pick anything that doesn't have the one bit. That's it, right? Simple. And hopefully you protect a group of most recently used cache block, right? You then protect a group of most recently used cache block. All right. Any questions? มีคำถามไหมครับ Oh, so great question. So question is, how do I determine which one is the most recently used, right? When I have a cache lookup, I access the cache. I would update this bit. I just look up this cache block. That cache block would be updated with this bit saying, hey, this is the most recently used, and you reset every other cache block bit. So let's say the next time you access this cache, you access this cache block. This cache block will be set to 1. Everything else will become 0, 0, 0. And this group will become 1. This becomes 0, 0, 0 again. So this way, right? This way you can keep updating the whole caching structure without the need to sort everything. You just update one bit and reset everything else. Setting and resetting in hardware is actually really simple, because imagine everything is connected by wires, right? When you want to set something to 0, you say, hey, set that to 0. One trigger, done. Much easier than sorting. Much easier than sorting. อันนี้ตอบคำถามไหมครับ Does it answer your question? So basically, when you have an access, you update the bit and reset everything else.
So there will be only one recently used block in each group.
Yes.
And there will be one recently used
This group. Most recently accessed
in
group.
all group.
Yeah, yeah.
And when it evict the cache in, let's say, the group 2, the most recently used block in the group 2 will not be evicted, right?
Yeah, it's like you get an immunity. Like, and anyone here watch like Survivor on like those games where you can compete and you get immunity. You don't get kicked out of the group. The same concept. If you just recently get updated or access, you get the immunity. You don't get kicked. ตอบคำถามปะครับหรือว่างงกว่าเดิม So does the explanation help, or are you still confused?
Yeah, I get it.
Okay, awesome. All right, so let me proceed forward, right? Because now we talk about the policy. Why do we do this? Because we want to avoid this problem called set thrashing. This is what happened when too many data map to the same set. We saw this problem already from the direct map cache example where you have address A and B, and you rotate between A and B and A and B and A and B. It just turned out go to the same set, so you screwed, right? So let's say what would happen if I have address, if I have a four-way cache, I use LRU, least recently used, and I go through access to address A, B, C, D, E, all mapped to the same cache set. When you do A, B, C, D, E, you can imagine A, B, C, D are in my cache. When I access E, which one do I kick out if I use LRU? If I use least recently used, which one is the least recently used between A, B, C, and D? If my access pattern is A, then B, then C, and then E, and then back to A again, and loop around this. Which one get kicked out to make the room for E? E would comes in, right? A is now the oldest. So A get kicks out, you replace A with E. Then you access A, because that's how you access, that's how you write the program. A comes in, look at, hey, is A in the cache? Nope. So I'm gonna kick out B, make a room for A. The next access is B, so B comes in, check if B in the cache, and you see, hey, B is not here. So let me replace C, which is the oldest block, with B. Then C comes in, and check if C is here. Nope. So you're gonna replace D with C. And then you have D coming in, because that's how you access A, B, C, D, and E, right? D comes in, check the whole caching structure, right? Nope, nothing is here. The least recently used access is E, so you get rid of E, replace it with C. My bad, replace it with D. And then the next access is E, you comes in, like node E here, you're gonna replace the oldest one, A, with E. And then this way, do you ever hit in the cache? No, you never really hit in a cache. In this way, if you pick anything at random, it's gonna be even more effective, right? You pick random block, guarantee. You have 5 access. You pick 4 random blocks, you're gonna get probably better than 50% hit rate. Right? So that's better than 0%. Right? So there are papers that talks about hybrid policy in order to combat against different behavior that come from the application. For example, there's an idea called set sampling. Set sampling basically do sample, should I use LYU? What's the hit rate? Should I use random? What's the hit rate? Compare them, pick the one that's better. So this is one of the paper at ISCA 2006. You can see how it evolved. Right now it's 2006. So I would say year 1995 to around late 2000. 2006, 2010. It's around when there's a lot of paper on caching and how to either improve the cost efficiency of the cache or improve the policy. Moin Qureshi is one of the people who work on this, basically on memory and on caching a lot. And right now, if you are interested about quantum computing, his group right now is actually, there's quite a handful of PhD students working on quantum computing as well. So feel free to check him out. He has a lot of great work that are published. So this work basically addresses the set thrashing problem, right? You either pick LYU or random. Another concept is called Belidy's optimal. So this is more like a theory side of things. The theory behind this policy is if you have black magic, so this is more theory, like if you have black magic, you can prove that the best policy is you evict the block that's going to be referenced the furthest by the program. When I said black magic, why is that the case? Because you need to predict the future. If you can predict the future, well, it's magic. You cannot. So there's a paper back in 1966. It's actually one of the really, really high impact paper because basically that's the goal of caching. And you want to be getting as close to the Belidy's optimal as possible. The problem is this is impossible to implement, right? So most of the time, the work in caching design are trying to simulate or imitate this policy. And another thing I want to discuss here is when you have a reflection policy, sometimes it doesn't improve the overall execution time because caching is only part of the hierarchy. There's many more things that can impact the overall access latency of your program, right? But let's continue on into what else can we do with the policy regarding cache? Because that's a quite large body of work on how to cache. The other thing you have to consider is the insertion policy. When you have a new cache block, right? When you have a new cache block, you can pick whether you want to insert at the most recently used. That would prevent this newly acquired blocks to be replaced. Or you can put it in the RIU position, right? Anyone have an idea on why, right? Why you might want to put in the RIU position? And make sure they get kicked out as soon as possible unless the next access is to this block. Why can that be useful? How many of you write a program where the address get accessed once and you never access it again afterward? Anyone here write a program that way? There was some part of your data that would have this behavior.มีใครเคยเขียนโปรแกรมแล้วมีแบบ array บางตัวที่แบบเราใช้ครั้งเดียวแล้วใช้ครั้งเดียวทิ้งอ่ะไม่ใช่เลย อ่านเสร็จจบพอเอามาทำอะไรสักอย่างหนึ่งแล้วก็จบมีใครเขียนโปรแกรมแล้วมันบาง data structure บางชิ้นอ่ะมันออกมาเป็นแบบนั้นมั้งครับมีไหมหรือว่าไม่มีแบบเรา stream data อ่านจบเสร็จSo actually this type of pattern can occur right, in your program. And when that happens, it means there's no reuse. There's no reuse for this particular piece of data. So sometimes it might be useful to put in an LIU position so that if there's no reuse, they get kicked out. So that's a trade-off, right? So there's a paper called RIP and DRIP, which is the paper that talks about insertion policy that many of the modern day CPU is trying to imitate this policy. So if you're curious, feel free to check it out. You can search Google RIP or DRIP cache insertion policy. Another thing that you have to talk about is promotion. Promotion means that I have access to the cache and it's a hit. What do I do with that cache block? Do I promote them to the MIU position most recently used, or do I leave it alone? When a cache block is accessed by the processor, do I promote them to the MIU? And that's actually most of the time it happens. Most of the, by default, right, the way you design the cache, when you have access to the cache block, you promote them to the MIU position. And this is done, as I showed earlier, by updating that bit. And this is the MIU bit. Most recently used, don't kick this block out because I just access it. I just access this, right? So that's it about the replacement and insertion policy. Any questions? มีคำถามไหมครับก่อนที่เราจะ move on ไปที่เรื่องการว่าถ้าเรามี update data update จะทำยังไงAny questions? Fair, all right, so it's just this is a long pause. So if there's no more question, the next thing I need to cover to make sure we still like have a hardware that correctly do things is what if you have a write? You write to a cache block. What happened? So when you write to a cache block, you need to think this way. The data change. The data change. So if you have the memory hierarchy, right? You have the CPU that write to L1. So data A prime, and then A prime replace the old data A. What happened here? At DRAM, we still have A, and L2 still have A, right? When you have update, It means that this update from A to A prime, right? You need to make sure you propagate this data to the higher level of the hierarchy. Otherwise, if someone try to access the L2 and say, hey, what's the data here? And you return A, you're going to return incorrect data, right? So this is basically handling of write. How do we update the same address that have new data? And in general, there are two policies. You can do what we call write through. Write through is, let's say you have CPU sending write to address X with A prime. So address X gets updated to A prime. So the L1, when this happened, the L1 would update X from A to A prime. And because it's write through, you update everything. So you send this update to L2, and then send this update to L3, send this update to DRAM. So everyone would have A prime. Everyone would have the most updated version of the data. What's the downside here? What's the downside of this policy? Let me ask you a flip question. Who reads? When I generate a read, where does it come from? ถ้าผมจะอ่าน address เนี้ยมันจะถูก generate จากฝั่งไหน ฝั่ง memory เป็นคน generate หรอ หรือว่าจริงๆมันเป็น instruction ใน CPU ที่เป็นคนจะอ่านค่า address x เนี่ยในอนาคต which one generate that read? The read in the future. The CPU, right? So when you do write through is simple, but it's actually will send a lot of update to DRAM. So this can be bandwidth intensive, right? Because if you think about it this way, let's say my code is something like this. Store A to X, then store A prime to X, and then store A double prime to X, and then you load X. What version does the load supposed to get? Do you get A or A prime or A double prime? A double prime, right? So if you care about A double prime, when you issue the load, when you issue this load instruction, because we have the cache, where do we look first? Where do we look first? Do we go directly to the DRAM or do we just go to L1? You go to L1, right? And because of the cache hierarchy, do I have a guarantee that, L1 would have A double prime? Because my store would first go to L1 as well, and it would update and make sure A double prime is there, right? So if you think about it, if you have a lot of store to the same address, store, you just, ideally you can just update the L1 and leave the update into L2 and L3 and DRAM later. You can be lazy. Why do you need to update if you know that my future access is going to check L1 first? This policy is called write back. Write back basically delay the update. Why? I guess when do I need to update L2? Let me ask you this question. When is the first time my load have to go to L2? The only case I'll go to L2 is what? Do I have to go to L2 if it's a hit in the L1? If it's a hit in the L1? Do I have to go to L2 if it's a miss in the L1? right? So if it's a miss in the L1, what does it mean? It means my cache block somehow get kicked out. Right? Someone kicked my block out because it's not in the L1 anymore. So when you replace a block, the write back policy will say, oh, okay, someone update the data, so let's update this data in L2 as well. The way you can tell whether you have to update the data or not is you have this dirty bits. The dirty bit, whenever you have update on the data, you flip the dirty bit from 0 into 1. When the dirty bit is 1 means that if I evict my cache block from L1 into L2, I would need to make sure I update my old version of the data in the L2. All right. And that way you save bandwidth and energy. You don't have to always update DRAM. All right. Is it clear? มีคำถามไหมครับสำหรับ write back policy? Any questions about the write back policy and what's the difference between write through, which update all the time, and write back, which do the update lazily? If not, then the next thing
นี่
ครับ
จะ
ครับอะไรครับ
คือ write back นี่จะอัปเดตก่อนที่จะเตะออกใช่ไหม
ก็จริงๆมันอัปเดตตอนเตะออกแล้วก็ได้ก็คือเวลาเรามี access ที่มันแบบเอา cache block ใหม่เข้ามาแล้วของเก่ามันเต็มอ่ะมันก็ต้องหยิบบล็อกหนึ่งที่เป็น victim แล้วถีบมันออกไปฮะไอ้บล็อกที่ถูกถีบออกไปอ่ะใน write back มันก็จะเช็คว่าdirty bit เป็น1หรือเปล่าถ้า dirty bit เป็น1แปลว่ามีใครสักคนอัปเดต data ในบล็อกเนี้ยเพราะฉะนั้นตอนเราถีบมันออกไปเราก็ต้องบอกว่าเฮ้ยอย่าลืมไปอัปเดต data ใน L2 นะเพราะเรายังไม่ได้อัปเดตเท่านั้นเองเพราะฉะนั้น process เนี้ยจะถูกทำตอน replacement ตอนที่เรามี replacement แล้วเราคลิกแบบ evict ไอ้บล็อกนี้ออกไปมันก็จะส่ง update request ไปที่ L2 yeah it writes to the same address right basically these all go to the same address which means it go to the same cache block which means that they go to the same location so does it hopefully that answered the question right awesome any other questions before we oh when the dirty bit get reset when you finish the update you update the dirty bits to be honest it never get reset because you kick the cache block out it's gone right the cache block is gone it's now in the lower level cache so it doesn't really get reset until you bring the data into the cache again so when you bring the data into the cache it starts with 0 and you have update it's flipped from 0 to 1 if it gets kicked out you check the value if it's still 0 no update so you don't have to do anything if it's 1 you update the data in the lower level cache to have the updated value okay get ไหมครับ all right so keep one little thing in mind this is single core this is single core we will have another separate lecture toward the end of this semester that talks about what about the write if you have multi-threaded on multiple core right but let's keep it single core simple write back and write through for now all right มีคำถามเพิ่มไหมครับ
มีคำถามเกี่ยวกับตัว Dirty Bit นะครับยังไม่ค่อยเคลียร์เท่าไหร่คือปกติ Dirty Bit สมมติว่าตอนแรกมันเริ่มมาทุกอันเป็น0หมดแล้วทีนี้มันจะต้องมีการเขียนทับไอ้ตรงบล็อกที่จะถูกเขียนทับเนี่ยมันจะถูกเซตเป็น1ใช่ไหมครับ
ใช่ครับ
แล้วมันก็จะ1ครั้งไปแบบนั้นจนถึงตอนไหนครับ
ก็มี2กรณีถ้าเป็น write through มันจะไม่มี dirty bit ถ้าเป็น write back กรณีเดียวที่เราจะอัปเดต data ใน cache level ต่อไปคืออะไร
ก็
คือตอน cache block
มี
ถูกถีบ
data
ออกไป
ใช่ครับ
พอ cache block ถูกถีบออกไปบล็อกนี้มันจะยังอยู่ใน cache ป่ะก็ไม่อยู่แล้วเพราะมันถูกถีบออกไปแล้วเพราะฉะนั้นพอมันเป็น1ปั๊บเนี่ยมันแค่บอกว่ามันเป็นการ notify cache อะว่าเฮ้ยอย่าลืมไปอัปเดต cache level ต่อไปด้วยนะแล้ว cache block ใหม่ที่เข้ามา cache block ใหม่ที่เข้ามา dirty bit มันก็จะเป็น0ก่อนคือการที่ dirty bit เป็น0มันแปลว่า data อันนี้คือ data ที่อัปเดตที่สุดของทุกๆ level ใน hierarchy ทุกๆ level address เนี้ยมีเวอร์ชันที่เป็นอัปเดตหมดถ้า dirty bit เป็น1ปั๊บแปลว่าอะไรแปลว่าเราอ่ะมีเวอร์ชันที่อัปเดตอยู่แต่เรายังไม่ได้บอกเพื่อนในการบอกว่าถ้าเราถูกถีบออกจาก cache block เนี่ยเราต้องไปบอกเพื่อนด้วยนะว่าให้อัปเดตด้วย
แล้วไอ้ dirty bit อะครับมันเก็บไว้ใน address ใช่ไหมครับ
เก็บไว้ในส่วนที่เป็น tag store ครับ
อ๋อแล้วสมมติว่ามันอยู่ L1 มี dirty bit เป็น1ณโมเมนต์ที่มันถูกถีบปึกเข้าไปที่ L2 ครับมันจะเปลี่ยน dirty bit เป็น0ป่ะครับถ้าเกิดมันมีของทับจาก L1 อีกทีมันค่อยเปลี่ยนเป็น1เพื่อผลักไปดีแล้ว
โอเคคำถามที่ดีถ้าเอาเดี๋ยวขอแยกเป็น2คำถามก่อนคำถามแรกก็คือพอมันถูกใส่เข้าไปใน L2 อัปเดตปั๊บมันต้องเปลี่ยน dirty bit หรือเปล่า
ครับ
จริงๆมันจะยังเป็น1อยู่เพราะอะไรเพราะเรายังไม่ได้อัปเดต DRAM ถ้าเราเปลี่ยนว่าเป็น0ปั๊บแล้วเราถูกถีบออกไปจาก L2 ปั๊บมันจะไม่รู้แล้วว่ามันต้องไปอัปเดต DRAM เพราะฉะนั้นเราต้อง maintain ไอ้ dirty bit อันนี้ไว้อันนี้คำถามแรกคำถามที่2ถ้าเรามี access มาจาก CPU ที่ไป cache block เนี้ยซึ่งมันอยู่ใน L2 แล้วจะเกิดอะไรขึ้นใช่ไหม
ครับ
มันก็จะไปฮิตอยู่ใน L2 มันจะไปฮิตอยู่ใน L2 เพราะฉะนั้นมันก็จะดึงบล็อกนี้กลับมาที่ L1 L1 ต้องเป็น dirty bit เป็น0หรือ1อันนี้
เป็น0แล้วครับ
เป็น0ใช่เพราะว่าตอนมันถูก replace เดี๋ยวเราไปเจอใน L2 เองเดี๋ยวเราไปเจอใน L2 เองแล้ว L2 จะมีค่าที่อัปเดตอยู่
เพราะว่า L2 มันค้างว่า1ไว้
ใช่ dirty bit มันจะบอกแค่ว่าเราต้องไปอัปเดตเลเวลต่อไปหรือเปล่า
ขอบคุณครับ
ครับโอเคคำถามดีมากชอบ alright so any other questions exactly yes so we keep right to L1 we're going to keep updating this data because if you think about it we have to make sure whenever we load we need to get the updated version the write back policy is just making sure we can lazily update things while guaranteeing that you will see the updated version of the data. All right, so the next thing I would like to talk about is, okay, we talk about write through and write back. The other thing that can happen is on a write, right? If you have a cache miss, you have a choice. Do we allocate the cache block? When you write, do we put that in a cache block? There are some policy, well, most of the policy would allocate, right? Basically put that block in the cache. Other policy was, hey, it's a write. I want to save space, so I don't want to put that in the cache. I leave it alone in DRAM. I don't do anything with it. If the cache write has low quality, sometimes write has lower low quality than read. In that case, maybe we'd leave it alone. We don't put them in the cache. So that's another design option. Most of the time, you would go with option 1. Do it the same way as the load. Treat it the same way. But remember that there's also this option of like, hey, maybe we don't put anything in the cache. And if you think about cache miss, right, there are 3 ways. There are 3 things that can happen that would cause a cache miss. The first type is compulsory miss. You've never seen the data before, so you cannot help it. The first time you see this address, you're gonna miss, right? Conflict miss is you go to the same set. Thrashing, right? Thrashing is what happened. You conflict in the same set. Even though you have the space left in another cache set, you have a miss because it goes to the same set and there are too many things mapped to the same set. Capacity miss is just as the name suggests, the cache is too small, right? The cache is too small to do everything. So there are multiple techniques in both hardware and software that can be used to address this problem, right? You can manage the data better. That can help the performance of the cache. You can prefetch. Prefetch means that I predict in the future I need to use this address, so I'm going to bring it to the cache ahead of time. And these kind of suggest at us, right, that we can measure the performance. How good is our cache design? So on top of the typical like execution time, how fast does my program run? Those are definitely important. But to measure the cache performance, you should also look at the hit rate and miss rate for each level of the cache. Do I improve the hit rate? I have the new design and everything is now in the cache, right? The cost of the hit and miss. If I hit, how long does it take to access my cache? If it's a cache miss, how long does it take to access my data? What's the total cost of a load, right? Let's say you have a load instruction. Let's say you have a load instruction. How long does it take to actually get my data? So basically, how long does it take for me to actually get the data, like for the CPU to get the data? And to improve the performance, you can first of all reduce the miss rate. You can increase associativity, make a better management, design replacement or insertion policy, or do prefetching. We'll cover prefetching in a bit. You can reduce the miss latency by adding more cache level. You can prioritize the critical load and store, right? Things that what caused my CPU to stall, right? You can do sub-blocking. If you're interested about this technique, basically now you break the cache block into sub-block, right? This is cache block. You then break into multiple sub-blocks where this happens. When you want to kick something out, so there's a sub-block, 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 and sub-block, you only kick this out and not the entire cache block. So you can try that too, right? You can have a better replacement or insertion policy. You can have multiple cache miss being handled in parallel. We'll learn about this when you talk about DRAM. You can actually handle a lot of cache miss in parallel. You can have multiple cache access per cycle, right? So these things can improve your hardware performance. And here are some examples of how important cache is. So let's take L1 take 2 cycle, L2 take 5, DRAM take 25 cycle, which is actually really fast. Typically, it's way more than 25. My program has 100 loads. I need to access the data 100 times. And then the hit rate of L1 and L2 is 80%. How long does it take for this? So can someone tell me how many cycles does it take to finish all these 100 loads? So for the 100 loads, right? All go access L1, so that takes 200 cycle. 80% finish getting the data in L1. The other 20%, which is 20 load, right? 20 loads. Access L2. That takes 100 more cycle. 80% finish that access in L2. 4 more, right? 20% of that, 4 more, 4 loads go to memory. And that also takes 100 more cycles. So in total, this is 400 cycles. Assuming that everything can be we do this back to back, right? Nothing can be done in parallel. In reality, you can maybe issue some of this in parallel. Any question about this example? มีคำถามไหมครับสำหรับตัวอย่างนี้ All right, so if there's no more question about this example, let's say the same system, right? L1 2 cycles, L2 5 cycles, L3 25 cycles. But you write the new program, same algorithm, but you issue way more loads. But when you issue these many loads, you try to make sure everything stay in L1 as much as possible. How long does it take? So to go to L1 alone, that's 2,000 cycles, right? Then 1% of those 1,000 loads, so 10 loads go to L2, that's 50 cycles. And then out of those 10, 2 of them have to go to DRAM, so that's another 50 cycles. So in total, there's 2,100 number of cycles. So when you write a program, right? When you write a program, one thing that you might want to be careful about is how many load and store you ended up doing. For each of the load and store, what's the hit rate? What's the hit rate, right? Because sometimes if the hit rate is good, typically they are good. But if you can somehow issue much fewer number of load and store for your application, it can be faster. For example, in this same setup, right? But the first 10 load go to L1, 50% is a hit. The other 5 loads go to L2, that's 25 cycle. And then 40% of those 5 loads hit in L2. So 3 more go into DRAM. So in total, it's only take 120 cycles, right? This 10 load takes only 120 cycles. So to wrap up, right? To wrap up, now that you know caching, right? To improve the performance of the program, one thing you want to do is to reduce the miss rate, right? To reduce the miss rate. What are the general things you can do? So for those of you who try to optimize your code for your research or your projects, when you're looping over large range of data, try to make it cache friendly, right? You can, if you want to multiply the metrics A and B, maybe you multiply row into another row, you transpose matrix B into B transpose so that when you multiply, it's actually much more cache friendly. You can loop over smaller size of the data so that it fit in the cache. So these are common techniques that most people in high performance computing area would deploy to make sure the program is really fast, right? How important are these type of program? We use it to, for example, predict the climate, right? So that we don't all die because of climate change, or at least we try. And these can be useful, right, to make the program faster. The other thing you need to remember is one cache block is multiple words. So when you access data sequentially, you're gonna have a lot of cache hits. If you access block by block by block by block, sometimes you end up with tons of cache misses if they map to the same set. The other thing you can do is to reduce the number of memory access, because memory access takes a long time to finish. Right? So these are the things that you should think about, and in order to make sure your program is fast, you might want to optimize your code based on how you use the cache, right? So I believe that many of you here use many of the modern libraries and API, right? How many of you never use any API calls that you downloaded and somehow make things faster? So many of the modern libraries, what they do is they would actually try to optimize performance. And one of the optimization is like based on the cache, right? Modern libraries can actually be used to squeeze out the performance of your program. So programmer in high performance computing community always look at the processor you're running with, and then it checks the cache size and the cache associativity, how many cache blocks in a set, and it the framework, the API, the library always try to make sure that all the time data access rarely have to go to DRAM, right? So the things that are typically done are divide and conquer, right? So for those of you who did algorithm or been through an algorithm class, you would know divide and conquer. So you would divide the data set so that it fits in the cache. Most library also try to prefetch the data. Prefetching means that, as I said again, predict what access do I want and try to grab that access ahead of time. Or they can remap the data so that they're spreading out to all the cache set so that you don't have a lot of conflict. And my kind of wrap up statement is cache hits really matter to performance. It really matters to performance. So that's it for the caching part. And now I'm going to transition into virtual memory. Any question about caching before we take another quick break before we transition into virtual memory, the intro part, and we will finish up virtual memory after the midterm. มีคำถามสำหรับ cache ไหมครับก่อนที่ผมจะ transition ไปที่ virtual memory
ผมตามตรง example ไม่ทันนะครับอาจารย์
อะไรนะครับ
ตามตรง example ไม่ทันนะครับขออีกรอบ
sample เมื่อกี้ใช่ไหมครับ
ใช่ตัวอย่างเดียวก็ได้ครับแต่แบบ
ได้ขอโทษทีไปเร็วไปหน่อยก็คือมันอันนี้ละกันเนาะก็คือจริงๆมันก็จับคูณหมดแหละอันนี้เรามีพันโหลดเราบอกว่า L1 ใช้2 cycle ถ้าเราจะต้องการไป access หรือไปหาว่าเราอยู่ใน L1 หรือเปล่าใช้2 cycle ไปหาใน L2 ใช้5ไปหาใน DRAM ใช้25เรามีพันโหลดอะทั้งพันโหลดมันต้องไปหาใน L1 ก่อนแน่นอนอันนี้ทุกคนเข้าใจกันเนาะคือสเต็ปแรกไปเช็คเลย L1 มีหรือเปล่าเพราะฉะนั้นการไปหาใน L1 ของทั้งพันโหลดเนี่ยมันใช้เลย by default 2,000 cycle เพราะมันต้องไปเช็คที่ L1 แล้วก็ถ้าเจอก็เย่เจอ2 cycle เจอ2 cycle เจอ2 cycle ไม่เจอใช้ไปแล้ว2 cycle เราต้องไปหาที่ L2 ต่อเสร็จแล้วจากพันโหลดถ้า hit rate ของ L1 เป็น 99% พันโหลดจะต้องไปที่ L2 กี่อันครับ
1998แล้ว
พันโหลด10%อยู่ 10%เอ้ยไม่ใช่ 1% ของ hit rate เป็น 99% แปลว่า miss 1% ก็คือมี10โหลดที่หลุดรอดไปต้องไปหาที่ L2
โอเค99% จาก 1,000 โหลดไม่ใช่ 2,000 บน L1
จาก 1,000 โหลดเพราะฉะนั้น10โหลดเนี้ยใช้เวลาเท่าไหร่เราก็ไปดูว่าL2 ถ้าจะเข้าไปดูว่าเจอไม่เจอเนี่ยใช้5 cycle เพราะฉะนั้น10โหลดนี้ก็จะใช้ไปอีก50 cycle
ครับ
แล้วก็เราก็บอกว่าL2 hit rate คือ 80% เพราะฉะนั้น10โหลดที่เราไปเนี่ย 80% จะ hit อีก 20% เป็น miss เพราะฉะนั้นอีก2โหลดมันจะหลุดรอดออกไว้ต้องไปหาที่ DRAM 2โหลดเนี่ยจะหลุดแล้วก็ต้องไปหาที่ DRAM ซึ่ง2โหลดนี้ใช้เวลาอีก50ก็ทั้งหมดก็ 2,100
โอเคครับ
Oh, that's a great question. So when you train the model in deep learning, the question is people usually set the mini batch size to be the power of 2 to the x. Does it have something to do with the optimizing caching? Depending on the number x, actually. So in your case, how big is that x?
Usually the batch size is something like, let's say, 8, 16, 32, 46.
Mm-hmm. So the lower number, it should fit in the lower level cache. If it's bigger number like 16, it would fit in maybe some of them would fit in the lower level cache. Some of them would fit in higher level cache. So the locality definitely should improve because it would kind of like perfectly fit, right? But when you go to 32 to 64, that's actually more about, hey, can I fit that in DRAM? But if you think about it, 32 is 4 gigabytes, right? Assuming that the batch size is 1 byte each, and for each entry, right? So 2 to the x, 2 to the 32 is 4 gigabytes, right? So that's quite a lot, but it still should fit in DRAM.
I
If
just
it's
wonder
64,
why. I just wonder why it have to be the power of 2 over x.
So my opinion, because I don't really know the what happened to the API that manage the data. So my really wild guess in terms of optimization is when you do this, it's easier to break things down because it's divisible by 2. So you can always like break things down in half and half and half and half so that things are fitting. But I'm not sure whether they did it or not. I'm not sure whether they did it or not. It might be just a configuration that's easy to scale, right? As you change from 8 to 9 to 10 to 16 to 32, it's easy to sweep over different value and see how it scale. So that can be the possibility as well. To be honest, I don't know enough about what is the algorithm in terms of optimization for this process ไม่รู้ว่าตอบคำถามหรือเปล่าเพราะว่าจริงๆมันก็ไม่ค่อยได้ตอบมากก็คือผมไม่แน่ใจว่าพาร์ทที่เป็น optimization เนี่ยเขาทำอะไรบ้างวันนี้มันขึ้นอยู่กับ library เนาะถ้าเป็น2กำลัง8อันนี้มันฟิตอยู่ใน cache แต่ถ้าเป็น2กำลัง16 12กำลัง16ก็ยังพอฟิตมันก็จะประมาณ32กิโลไบต์เอ้ย2กำลัง
10ผมหมายถึงไอ้8632นี่คือเป็นผลลัพธ์ของ2กำลัง x แล้วครับไม่ใช่
ถ้าอย่างนั้นยังไงก็ฟิตใน cache ก็อย่างนั้นก็คือจริงๆมันฟิตอยู่แล้วอย่างนั้นก็คือยังไงก็จะแบบ locality ก็จะดีมากเพราะว่าไซส์ของ cache ส่วนมากก็เป็น format ของ2กำลัง x เหมือนกันมันทำให้เราสามารถฟิตหลายๆ mini batch ได้ด้วยคือมันไม่ใช่แค่แบบฟิตแค่อันเดียวด้วยความที่มันเป็น2กำลัง x มันจะฟิตหลายๆอันโดยที่ไม่มีเศษเหลือพอมันไม่มีเศษเหลือแหว่งๆเนี่ยมันจะ iterate ง่ายกว่าแล้วทุกอย่างก็จะอยู่ใน cache ผมนึกว่า x คือ8 16 32 64ว่าถ้า x คือ64เริ่มใหญ่บัก x แล้ว มันจะใหญ่มากคือ8กับ16เนี่ยถ้าเป็น2กำลัง8 2ถึง2กำลัง16ยังพอได้อยู่พวกนั้นก็เป็นหลักกิโลไบต์32ก็กิกะไบต์4กิกก็ยังอยู่ใน DRAM อะไรอย่างนี้แต่ถ้าบอกว่าเป็น flat 2กำลัง3 2กำลัง4 2กำลัง5อย่างเงี้ยก็อย่างพวกเนี้ยฟิตใน cache อยู่ละไม่รู้อันนี้ในตอบถาม
จริงๆมันขึ้นอยู่กับว่าไซส์ของแซมเปิลหนึ่งมันใหญ่เท่าไหร่ด้วยครับบางทีแค่8แซมเปิลมันก็อาจจะกินไปเป็น10กิกแล้วก็ได้
ส่วนมากเขาจะทำ tiling ให้มันแบบเล็กที่สุดเท่าที่จะทำได้แต่ถ้าแซมเปิลใหญ่มันก็ต้องทำหลายรอบไงคือมันมีเวลาผม config ไอ้พวก mini batch size อะเวลาสมมติเวลาผมทำวิจัยฝั่ง architecture เนาะคือเราบางทีก็ใช้ workload พวกนี้ในการ drive hardware ว่าเอ้ยนี่เห็นไหม run machine learning deep learning เร็วขึ้นแหละผมก็จะพยายาม sweep ดูว่ามันมี mini batch size เนี่ยมีขนาดแต่ละขนาดมีผลอะไรกับ policy เราหรือเปล่าแล้วส่วนมากที่เห็นเนี่ยก็คือว่ามันจะมีแบบมันจะเป็นอย่างเงี้ยมันจะดีขึ้นแล้วพอแบบเยิ่มใหญ่ก็ไม่ดีแล้วอย่างเงี้ยครับมันก็จะมีจุดที่ค่อนข้างจะ optimal อยู่แล้วที่เห็นเนี่ยก็คือ cache ก็มีผลอย่างหนึ่งเพราะว่าถ้ามันใหญ่เกินมันไม่อยู่ใน cache อีกแล้วแต่ถ้ามันเล็กเกินมันต้องทำหลายรอบถ้าผมจำไม่ผิดนะแต่อันนี้ผมไม่แน่ใจคือมันต้องทำหลายรอบใช่ไหมถ้ามันเล็ก
ใช่ครับ
พอมันต้องทำหลายรอบฝั่งที่เป็น compute มันจะเริ่มเยอะเพราะว่า CPU ต้องทำงานเยอะแต่ถ้ามันใหญ่เกินCPU ไม่ต้องทำงานเยอะแต่ cache locality อุบาทมากโอเคมีคำถามอะไรเพิ่มไหมครับ All right, so if there's no more questions, let's do another 5 minutes break. We'll meet again at 3:37. We will do a little bit of an introduction of why do we need virtual memory and what's the benefit, right? One thing I want to also stress over this topic is this is one of the topic that I did a lot of research on. my thesis revolved around two things: GPU and virtual memory design for these type of processor. So I do a lot of VM research. I do a lot of research on GPU. So these are some of the things that you have a lot of questions, if you have a lot of curiosity about, like, hey, what does people are doing in cloud, in server, in like, what did I learn from my internship, for example, at VMware Research? I would be more than willing to share these things. All right. It's one of the topics that's much closer to home for me. This is basically my toy, my fun in research. So we'll do a 5 minutes break. We'll come back at 3:37 and we quickly resume and talk about why do we need virtual memory. All right, before we kind of conclude the class. โอเคนะครับ ขอเดี๋ยวเบรก5 นาทีละกัน จะได้ switch topic โดยที่ไม่เหมือนมาก เดี๋ยวอีก5 นาทีเจอกันนะครับฮัลโหลกลับมากันยังครับฮัลโหล All right, one thumbs up. I assume that only one thumbs up means everyone's back. So let's continue on to the last, I guess, part of the topic that we're gonna finish today and continue on to next week. Virtual memory, right? So let me motivate why this is a thing that you need to know. How many people here know or heard about this word, virtual memory, before? Can you raise your hand if you heard about this before? All right, good and bad, right? Awesome. That's one of you who heard about it. The two of you who heard about it before. The rest, if I think you might have heard about it in one of the undergraduate class. If you have not heard about it, again, perfect time to learn. I'm glad that I make the slides making an assumption that let's start from nothing and build it up. So why do you want virtual memory? Again, let's go back to the goal of memory. Like, this is what we want. We want something that would give you unlimited memory. Magical, right? We want to be able to have unlimited memory. We want to also make sure every single program has a virtual view of your own memory. Why? Why is that the case? Think about when you run, how many people here run at least 5 to 10 applications at a time? How many? I mean, I'm sure you guys are. Did you realize that in your program, how many of you open Task Manager or look at the number of processes running on your computer before? Or like when computer hangs, you do Control Alternate Delete, look at Task Manager. What do you see? There's a bunch of tasks, a bunch of programs running, right? Countless of programs are running at the same time. So think about, let's say there's 10 applications running. Each one of them occupied a certain region in the main memory. From the programmer point of view, you want to make sure you don't have to worry about where are the other process memory are, right? Unless you're working with something that doesn't have virtual memory. But you need a notion of this is where you can work on. This is where the memory that you have is, right? So that you don't have to worry about, okay, can I use that address? Can I use that address? Can I use the other address? Right? That would be a hell to program something like that. It would be hell. You want to make sure that you have control over how you want to use your own address. And that should be automatic, right? That should be automatic. Virtual memory gives you the first bullet point, the notion of almost unlimited memory. It gives you the virtual view of your own memory. It also allows, right, when you have multiple programs running, it also allows memory protection. It basically means that when you have two applications running in parallel, one application should not be able to read and write into the other application's data. Otherwise, you're basically writing a virus for your computer. You should not be able to read or write into someone else's data. And the user should not be able to read or write into kernel's data as well, right? Virtual memory is there to protect you. It's called memory protection. So what exactly is virtual memory? Okay, what exactly is virtual memory? When you write a program in Python, Java, C, right? Oh, what is kernel? Okay, great question. So kernel is, the word means a core, right? Core of something. Core of something. So let's say I give you a computer without the operating system. How are you going to use the computer? I give you a computer with nothing else. Anyone here have like experience writing a basic operating system before at all? Like anyone here tried that before? So if you have not, right? one thing I can explain to you. When you have new GPU, you have to install driver, right? When you have a new hard drive, you have to make sure the SATA interface work with the hard drive. Kernels are, I guess, pieces of computer program, but this doesn't really give you the application in the sense that you use it, but it allow you to utilize the computer. Basically, it allow you to not just driving the hardware, provide interface with the user, providing way to communicate between inputs and outputs and all the parts in your program. It is a core. It's a core software for your computer. Sometimes we call this system software. It's a software for your computer system. The OS has the kernel that drives your machine, right? That drive your machine. So hopefully that answered the question somewhat, right? Is it more clear about that? Basically, what I mean here is, if I write my application, I should not be able to see something the data from the OS, right? that I'm not supposed to be able to access. All right. So then, what exactly is virtual memory? Basically, when you write a program, every single piece of the data you're writing, those are virtual address. But the data itself has to be located somewhere in your DRAM, right? Somewhere in your DRAM. So think about it this way. The data you're using, physically, it has to be electrons in some location of your DRAM. It has to be some of those electrons in DRAM. That's the physical address. The address to find those set of electrons are the physical address. But when you write a program, the address that you see as a programmer is a virtual address. And both system and hardware basically work together to translate basically the virtual address that the programmer see to the real location of those electrons inside your computer, right? So the first benefit is when you have virtual memory, when you program, you're gonna have your own virtual space. You don't have to worry about someone else. You don't have to worry, hey, is that someone else's electron? Everything you access is your own, right? And then the other benefit is, how can you have unlimited memory? So technically it is limited, right? There are ways to create this illusion. Typically how big is your hard drive? How big is your hard drive? Terabytes, right? It can be, I don't know, 500 gigabytes. It can be 2 terabytes. So the key idea of giving the notion of unlimited memory. Anyone heard about this word swap? When you look at Task Manager or look at when you type in top on your computer in a MacBook or Linux, it will tell you how much of the data is in swap. Anyone see this word before? So for those of you who've seen that word before, these are the region in your disk that are used to extend the memory. What's the bad thing about this? What if you have a lot of things in swap? What would happen? Hard drive is way slower. When you have the memory, you're talking about something like maybe 12 nanosecond to maybe 200 nanosecond. When you talk about hard drive, it's not nanosecond anymore. It's hundreds of microseconds or milliseconds of the access latency. So going to swap takes a long time. But having this extensible area allow you to create a much bigger space that your memory has. This can be done through the page table structure, right? And that's the second benefit So a page is essentially a range of address. Typically, these are 4 kilobytes, and it can be much larger. And again, we kind of wrap it up now because we're running out of time. Next week, by the way, we need to make sure there is an exam, right? Hopefully you guys are prepared. So let me say something before we leave today. Exam next week, I will release at around because next week there's a holiday in the middle, so I hope that you get some break, right? The reason why I do this, you are going to have Monday, Tuesday, Wednesday, Thursday, and Friday all to work on it. It should be able to finish within 3 hours. So my recommendation is to block out at least maybe 5 hours of your time in that week so that you can, first of all, take a look at the exam. If there are any clarification questions, let me know. Let me know. Right now, I'm going to allocate Tuesday 4 to 6 to be a Q&A. And if we need more, I'm going to do 1 more hour on either Thursday or hopefully not Friday because it's a little bit too late for the clarification question. Is that okay for the logistic for our exam? โอเคไหมครับ logistic แบบนี้ให้ไปเลย5 วันมันควรจะไม่ใช้ไม่เกิน5 ชั่วโมงเอาจริงๆแล้วตอนถ้าผมทำเองก็คือผมรู้คำตอบเนาะก็คือใช้เวลาประมาณชั่วโมงนึงไม่ได้ยาวมากไม่ได้ยาวมากหวังว่าไม่ได้ยากมากด้วยก็เดี๋ยวก็นี่แหละ format and the next thing is I think we already did this so for those of you who want to do lab 3 do you need lab 3 starter or do you have a functional lab 2 already มีใครอยากจะต้องการเอา lab starter lab 3บ้างครับเพราะว่าจริงๆมันก็คือคำตอบ lab 2มันคือ starter lab 3น้องที่จะทำ lab 3 okay so in that case I have your board you can choose there are multiple options right you can pick whatever day you want that day will be the day I release lab 3 starter because it's a solution for lab 2 so lab 2 due date will be the day I release lab 3 starter because that's a solution for lab 2 so pick your date so can you work with your friends and see what they work for you like people here in the class basically pick what day would work for you because I want to make sure lab 2 you have like I want to make sure you have the option to like basically take your time to make sure you can implement what is required for lab 2 but if you delay this too long your downside is like you would have to start a code way too late to implement everything in lab 3 right my suggestion maybe the end of month would it work for you guys maybe like the end of October okay so many thumbs up so let me check the calendar and what day works so how about the midnight of 27 so let's pick that for now and we can negotiate later so if you kind of like fight among yourselves and see which one would work better let me know all right One last thing, I'm gonna organize I think you've seen this already on the announcement. So I'm working with Thai SC, which is basically a supercomputer center ของสวทช. And we'll have the basic GPU architecture and CUDA programming and how to use profiling tools as a workshop with NVIDIA. So I'm gonna talk. So the workshop is 2 hours. Dr. Itikan, which is the chief technology director of the Southeast Asia at NVIDIA, will opening up maybe 10 minutes in the beginning, and I'll take over. The workshop will be in Thai. The workshop will be in Thai. I will talk about the GPU architecture. How does it work? Why does it work well with certain programs? And then Dr. Pat, which is another expert on GPU, would come in and talk about CUDA optimization. How do you profile? So for those of you who are working on like profiling tools, I definitely recommend to like at least consider joining this workshop. I'll explain why the GPU work. Dr. Pat will explain how to optimize performance. This is really introductory, right? So the motivation behind this is three of us were basically talking that, hey, there's quite a lot of people who have been using PyTorch, TensorFlow to write code on a GPU, but then it's still GPU optimization and performance optimization and writing CUDA is still a really, really big gap amongst like a typical engineer in Thailand and everywhere else in the world that they know how to use the GPU. Right, so we basically say, hey, let's organize this series of workshops starting from this one, which is the introductory workshop that we can gather people who might be interested at this kind of topic. So that we see, hey, these are the tools that you can use, and then we will actually start to organize more like intermediate level and advanced workshop for these kind of events in the future, so that we have engineers who knows how to program in CUDA, who knows how to optimize the code, and who know how to identify bottlenecks on GPU computing. So if you're interested, just scan. So there's a sign up link on the announcement. You can scan the QR code from this poster as well. And yeah, so that's it. ขอโทษทีที่มี self advertisement นิดหน่อยสำหรับเวิร์กช็อปนี้ก็คือผมอยากจะให้ community ในประเทศไทยอ่ะคือไม่ใช่แค่แบบโยนอะไรก็ไม่รู้ใส่ GPU แล้วก็แบบรันดีไม่ดีอะไรก็ว่าไปแต่อยากจะให้แบบ optimize มันเป็นด้วยแบบไม่ใช่คิดอะไร คิดอะไรไม่ออกซื้อ GPU ใหม่อะไรเงี้ยคือบางทีถ้าเราไม่ได้ใช้ resource ทั้งหมดบน GPU อ่ะถึงซื้ออันใหม่มันก็ไม่ได้เร็วขึ้นอย่างนี้เนาะคือซื้ออันใหม่มันก็ไม่ได้เร็วขึ้นเพราะว่า bottleneck ไม่ได้อยู่ที่ resource bottleneck มันอยู่ที่ algorithm หรือเปล่า bottleneck มันอยู่ที่ตรงไหนสักอย่างใน GPU เราหรือเปล่าอะไรเงี้ยครับแล้วก็ผมอยากจะlecture เรื่อง architecture ด้วยก็คือมันดีไซน์ GPU เนี่ยเราดีไซน์มายังไงทำไมมันถึงเร็วสำหรับบาง workload ทำไมมันถึงช้าโคตรสำหรับบาง workload อะไรเหมาะกับการรันบน GPU อะไรไม่เหมาะอะไรเงี้ยครับก็เดี๋ยวจะ cover กันวันที่15ก็ถ้าสนใจจอยได้นะครับแค่นี้แหละครับมีคำถามอะไรหรือเปล่า Any last minute questions
ก็จะถามเกี่ยวกับคำแนะนำครับ
เดี๋ยวแป๊บนึงนะครับมีถามเกี่ยวกับกันบ้าน so that's the last day to submit lab 2 I cannot release lab 3 starter code because you can take the starter code and submit as lab 2 basically lab 2 starter code for lab 3 is lab 2 solution. So hopefully that's clear. So that will be 27 plus the additional possible late days. After that, I'm going to post the starter code for lab 3. Is that okay? โอเคครับเมื่อกี้คำถามคืออะไรนะครับ
อ๋อครับผมไปลองเขาเรียกว่าอะไรNray Proof กับ CUDA 11 กับRTX 3090นะครับแล้ว Nray Proof มัน deprecate ไปแล้ว
ใช่มันจะใช้เป็นVisual Profiler แทน
ครับทีนี้ไปลองกับเหมือนเป็น CUDA CLI Visual Profiler ครับมันร้องบอกว่าไม่ support 3090 RTX
แต่มันจะมีโปรไฟล์ตัวใหม่นี่จำไม่ผิด
อ๋ออาจจะรบกวนอาจารย์แปะเวอร์ชันหรือ
ได้
อะไร
เดี๋ยวเอางี้เดี๋ยวผมแปะเข้าไปใน announcement ดีกว่าเนาะ
ครับ
แต่เพราะว่ามีหลายน้องหน่อยหลายโปรเจกต์ใช้อยู่เดี๋ยว announcement อีกอันหนึ่งคือผมถามนิดนึงว่าไอตัว Discord ที่ใช้กันอยู่เนี่ยคือมีอาจารย์คือแบบว่าถ้าผมไปแจมเนี่ยจะว่าอะไรหรือเปล่าหรือว่าแบบอยากให้เป็นนักเรียนเท่านั้นอะไรอย่างงี้ผมไม่รู้หรือเดี๋ยวผมถามน้องๆที่ฟิตเทคคือเอางี้ก็คือสาเหตุที่ผมถามเพราะว่าอย่างมันมีหลายกรณีเนาะอย่างที่ตอนที่ผมไปสอนที่มหิดลใช่ไหมทาง MUIC อ่ะเขามี Discord ของเขาเลยแล้วทุกคนก็อยู่ในนั้นคือแบบนักเรียนอาจารย์อะไรก็แบบมีช่องชวนกินช่องเล่นเกมช่องถามกันบ้านอะไรเงี้ยครับแต่ว่าผมไม่รู้เพราะว่าบางที่เขาก็จะแบบอันนี้อยากให้เป็นเซิร์ฟเวอร์สำหรับนักเรียนเท่านั้นเพราะว่าเผื่อเขินอะไรเงี้ยคือผมก็ไม่แน่ใจว่าวิธีไหนดีที่สุดสำหรับการสร้าง channel ในการ communicate กันนะผมรู้สึกส่วนตัวนะผมคิดว่าอีเมลมันโอเค Canvas มันโอเคแต่มันมีวิธีที่ดีกว่านั้นเดี๋ยวใช่โดยเฉพาะเวลาเราเริ่ม kick off project แล้วแล้วมีโปรเจกต์หลายๆคนที่ทำอะไรคล้ายๆกันจะได้มา discuss กันก็เลยเดี๋ยวรบกวนอาจจะน้องกลุ่มเนี้ยมาลองคิดนิดนึงว่าเราจะหา channel ไหนดีอยากได้ channel แบบไหนแล้วก็มาบอกผมเพราะว่าผมจะได้สร้าง channel แบบนั้นให้ได้ไหมครับเนี่ยจะคุยกันในแชทนี้ก็ได้หมายถึงว่าแบบทำวิธีไหนก็ได้คือแบบเดี๋ยวสักสัปดาห์หน้าเดี๋ยวผมขอแบบไกด์ไลน์หรือคำตอบคร่าวๆนิดนึงก็ยังดีว่าวิธีไหนที่จะคอมมิวนิเคตกับน้องทุกคนได้สะดวกที่สุดได้ไหมถ้า Discord ก็ดีก็ได้เลยครับก็เดี๋ยวแค่งั้นก็บอกมาว่าจะแบบจะให้ไปใช้เซิร์ฟเวอร์ที่ไหนหรือจะให้ผมสร้างเซิร์ฟเวอร์เองได้ทั้งคู่งั้นมีคำถามอะไรเพิ่มไหมครับ
ผมว่าในส่วนของ Discord ผมว่าไม่ได้มี Discord อะไรที่เราใช้แบบทั่วไปทั้งมหาวิทยาลัยแต่ว่าอีเวนต์ทั้งภาควิชาขนาดนั้นนะครับ Discord ที่ผมใช้ก็จะมีแค่ใน lab อะไรอย่างเงี้ยครับเพราะฉะนั้น
โอเคเข้าใจแล้วครับ
คิดว่าน่าจะสร้างใหม่อาจารย์สร้างใหม่น่าจะตอบโจทย์เหมือนกัน
งั้นเดี๋ยวผมอาจจะสร้างใหม่ดีกว่า
ครับผม
ได้
เป็นยังไง
โอเคครับ
ที่นี่ไม่ได้ใช้ Discord คุยกันทั้งทั่วไปขนาดนั้น
เข้าใจแล้วโอเคครับได้เลยยินดีเอางี้ส่วนตัวผมเนี่ยผมแบบวิธีไหนก็ได้เอาที่มันแบบ effective ที่สุดสำหรับเราทุกคนเนาะเราไม่มี tradition อะไรทั้งนั้นเราไม่สนไม่แคร์ทำยังไงก็ได้ให้ทุกอย่างมันเวิร์กจบ tradition มันทำลายประเทศเรามามากพอโอเคครับนี่ผม ผมต้องทิ้งท้ายด้วยกันบ่นทุกครับโอเคมีคำถามอะไรเพิ่มเติมไหมครับเดี๋ยวรบกวนน้องที่กดอ่านก็เหมือนเดิมอาจจะรบกวนเอาเข้า SharePoint หน่อยแล้วเดี๋ยวผมอัปโหลดให้นะครับ